we'll get started. A few sort of words of introduction before we start. So that's me. I'm Richard Eisenberg, and I spend quite a bit of time thinking about dependent types and Haskell. We'll talk more about that actually toward the end of the talk. The other stuff, it surprisingly doesn't have as many dependent types. Also, if any of you were at ZuraHack this spring, this is the same talk that I gave there. You were welcome to get up and go to something else. I was just asked this morning, as we heard this morning, right? The original speaker for this slot is unwell today, and so I sort of jumped in at the last minute. So that means, one, it is a recycled talk, but two, I have not rehearsed this since June, and so if I get a little confused at my slides, please forgive me. And sort of as advertised, it's not quite a workshop. It's more of a talk. I very much want questions, but I don't have like exercises for you all to get out your laptops and do, as I would if I had sort of prepped this as a workshop. So that's just a few disclaimers. But please do ask questions. So the talk is shorter than the time that we have allotted. So there's plenty of time for questions. So you'll see here a link. Has anyone actually tried this link? Yes. Does it work? No, it 404s. That's very interesting. That's really too bad. What can I do about that very quickly? Just give the talk, I think. I think that's probably a good idea. Okay, I will, if there's a dry moment somewhere toward the end, I will make that available. I don't know why that would happen. Okay, so whenever I get a chance to actually get some feedback. So Simon talked this morning about there's no telemetry, right? So we don't know how people use Haskell. So I love to get a little feedback whenever I get a chance to give a talk. So how many of you use Haskell to make money in some way? Wow, that's amazing. So I assume most of you, maybe I won't call out to ask for raises of hands here, but that you're working for someone else, or you're working for yourself. You sort of have a business, but it's not just sort of something that you do in your spare time if you're using it to make money. So that's pretty cool. So one of the things I find really fun about these kinds of events is seeing people who use Haskell to write web services and use Haskell. I'm fascinated by the fact that every now and then I see Habito advertise on television, right? And I know that there's like Haskell powering that, but sort of behind the scenes, probably not the ad, but so very exciting to do something like this. So I want us to start off with sort of a history of Haskell's type system. Actually, this is before Haskell. Haskell was 1990, but this is sort of along with the birth of Haskell. So we have, Haskell started out with, well, there's type classes, right? We wanted some way to be able to use a plus sign and have it mean different things depending on what types of numbers we're using. And so it's like, oh, okay, so we can do that in a more principled way, say, than Java or C++ does it. That we can have this type class approach. And then we got up to functional dependencies. So I realized there's a long gap between these. And then we realized that once we wanted to have multi-parameter type classes, that would sort of go in between these, that you want to have some way of one type parameter or one parameter to the type class affecting another. And so that gives us functional dependencies. And that, I think, in my opinion, that was sort of the genie first starting to crawl out of the bottle, right? Once we could do this, then suddenly we could do some level of computation in types. So this got explored more deeply with data families. So data families actually were invented as a way to make programs run faster. That we wanted to have specialized representations for, say, arrays of ints. Right? We can do that really fast. If we have an array of some other type, maybe we can't do it as fast. So data families are a way to do that. Then these got generalized a little bit further to type families. So now we really had things that acted as functions on types. And so this was in some ways a competitor to functional dependencies, and the two are still sort of fighting it out today, actually. From these, then we have generalized algebraic data types. So generalized algebraic data types allow us to sort of control the type of an algebraic data type depending on what constructor we use. Or conversely, when we pattern match on a constructor, we get to learn something about the type. So with GADTs, in my opinion, the genie crawled a little bit further out of the bottle here, right? Now we can have programs that when they take a runtime action, they cause sort of compile time information to become available. And so that means different parts of a case statement can have different types. So that was 3 big papers all right in a row. And then there's this gap here. And so lots of stuff happened in that time, one of them being a complete re-implementation of the type checker in GHC to accommodate these new innovations. So then this is about where I started studying Haskell. It was in 2011. So data type promotion came along, and now what that means is that we can use data constructors in types, and we can use sort of types in kinds. And that opened up better expressivity, better checking of all of this type level programming. So then we have, right after that, we had singletons, which isn't really a Haskell feature, but it's something that's used to sort of pretend that we have dependent types. So there was a lot of this that was sort of out there in the folklore, and I tried to sort of pull it together in this paper in 2012. So then another big step forward, in my opinion, is the idea of type in type. So previously, there were terms, and there were types, and there were kinds, and they were all sort of separate. Now, since GHC 8.0, it took some years to implement this, since GHC 8.0, we've had types and kinds being the same thing. And so that means not only can we have functions on types, but we can have functions on kinds. And as Simon likes to remind me, we're still sort of recovering from this big sea change inside of GHC. This made things a bit more complicated, but a lot more expressive. So we also now have closed type families. So open type families are sort of like class methods almost. Closed type families are more like proper functions. And so we can do a little bit more computation in types. All of this led to problems because now that we had all of these fun types, we wanted to be able to do complete pattern matches. So as Simon explained to us this morning, this is hard. And so here was a nice paper that refined the pattern match warning checker. We're still clearly working on that, as Simon explained this morning. Not only do we want closed type families, but we sometimes want to be able to propagate information from results of type families back to the argument, so we have injective type families. Sometimes all these implicits are hard to work with, so we want type application. We want to be able to tell GHC how we're specializing some function instead of having it infer. All of these tools can be used quite usefully to have type reflection. So there's this typable mechanism, which allows us essentially to do dynamic typing in a statically typed language. And so that's built on a bunch of the previous extensions. We have pattern synonyms now, so we can abstract over patterns, and they have their own complex relationships with types. We recently have quantified class constraints, meaning not only do we have a class constraint, but we can then say that this is true for any type A, not just for a specific type A. More recently, this one is not yet implemented. It's in progress. We have the idea of type abstractions, so that way we can have a part of our code that is generalized over a certain type variable. So a few things to comment here. First off, I could make another whole slide this dense with more papers about Haskell and Haskell's type system. The other observation is, I mean, how wonderful it is that we have this language that sort of every major step is accompanied by peer-reviewed research. I just think that's so fantastic because it means that we have long-form documentation of our decisions, and it allows us to really sort of understand where we are and where we're going. And we have a little bit more faith that things are right when everything is sort of goes through the peer review process. So what this talk is really about is, with all of this explosion, how can we make use of it? Where does all of this go to? How can we make use of it? So just a quick question. How many people here were in Marco's talk this morning about keeping Haskell simple? Oh, OK, wow, not a big overlap between that and this. something to be said about that, actually. So I want to return to that because there's, well, not many people were there, but I'll return to that. So this talk is really about Stitch. So Stitch stands for the Sound Type Indexed Type Checker, and it's an application of all of this technology to something fairly typical. So the idea is that I've implemented a simply typed lambda calculus. So, a criticism at this point is, well, you type system researchers, why do you always just implement the simply typed lambda calculus, right? Why don't you do something useful? So I would argue, first off, implementing the simply typed lambda calculus is really useful, right? Large systems all have implementations of some sort of scripting language, right? Whether it's a productivity suite, right? We know Microsoft Word, Microsoft Excel are all scriptable. Whether it's something, any text editor, you have a way of scripting that. Games have a way of scripting them. There's been several talks today about build systems. Those are run by scripts, right? So implementing a language is actually a fairly common phenomenon. And the other nice thing about this example is it's something that we're all familiar with. We know the lambda calculus. Even if you've never heard of the lambda calculus before, if you've programmed Haskell, you know the lambda calculus. It's a way of defining these anonymous functions and applying them. So let me sort of go over and show you what this looks like. And I'm going to have to fuss a little bit with the display here. Does that? There we go. That's what it should look like. OK. I can make that bigger. OK, so hopefully this does something. Yes, good. So here it is. The one point I'd like to make is we're going to see a lot of fancy code, but this is actually just an application that runs, right? Anyone can download this and run it, and I've actually used this to teach undergrads about the lambda calculus. I've not shown them the code. The code is a little bit more intricate, but the end application is just an application. And so it can evaluate 4. That's not a big surprise. It can evaluate 4 plus 6. So we see here that it knows the types of things, right? We can see that it gives a type to everything. And it's a lambda calculus, so I can do something like this. Right? So I can write a little lambda function. I do have to annotate the type of the bound variable. There is no type inference in this yet, although I think it would be quite possible to do and fun. So that may happen someday. And it's higher order, so I can do things. So here I can take a function from int to int and then an argument and apply that function to that argument twice. And then I can have a function that adds 2 and then apply all of that to 8, and I get 12. Right? So this is all sort of like GHCI. It's not all that exciting. But one fun thing it can do is I can ask for how this steps. So here we can see using sort of a small step reduction. So again, this is used in an academic environment to teach students about lambda calculus, is we can see how this would reduce from the beginning to the end. So one thing that we see in the output now is that there's these funny hash signs, right? So my initial input has F's and X's in it. But that's all gone for these indices. How many people in here know what a de Bruijn index is? Wow, OK. I'd just like to reflect on the fact that we have a room full of people, many of whom raise their hands for they use Haskell for money, so you're actual developers, and who know de Bruijn indices. This is very cool. So we'll return to that in a moment. But the bottom line is that you can just sort of guide yourself by the colors. So when you see a yellow hash sign, that's going to match up with the yellow variable, and the green hash sign matches up with the green variable, and so on. So we can see how this reduces. So that's sort of what this looks like on the outside. But the evidence here, the reason I'm showing this is that there's a parser, there's an evaluator, there's a pretty printer. It's all the stuff that you want. OK, so now we have to fuss with the displays again for a moment. And hopefully it ends up the right way. Yes, OK, cool. OK, so for those of you that don't know about de Bruijn indices, it's a way of keeping track of variables so that we don't have to worry about their names, right? Of course, in my example there, I chose F and I chose X, but those names are irrelevant. And when I'm computing, I don't really want to have these extra irrelevant things cluttering up my data structure. And so instead, what we do is we want to, a de Bruijn index counts the number of intervening binders between a variable binding and its occurrence. So what on earth does that mean? So that means that here we have 0, and we see that it's yellow, and that means that it looks for the thing that's bound with no lambdas in between. So that's this one, 0 lambdas in between the usage site and the binding site. For 1 here, there is 1 lambda that appears between the usage site and the binding site. So the 0 and the 1 indicate that, but one of the challenges with de Bruijn indices is that they're hard to keep track of, and so I've used colors in the output here. And that's sort of a small innovation, but I've actually gotten a bunch of people to say that that just makes a whole lot more sense when there's colors involved. OK, so I guess I did that with my finger, but the slides have it as well. So, and we can see that the structure in the de Bruijn indices matches the structure that I wrote in my initial code. OK, let me just pause here. Are there questions so far? OK, we're good. So why do I use de Bruijn indices? Why don't I just use names? So one is I don't have to worry about things like shadowing, right? Shadowing would be if I bind the same variable x twice, then there's a lot of fussing to do. It's not very fun. These names, as I said, are meaningless anyway. And the real reason is that it's much easier to build a system in the way that I have using de Bruijn indices. One could contemplate doing other things, but that would take even more pyrotechnics than we have here. The real reason, in my opinion, not to use de Bruijn indices is that they're hard for humans. But my hope is that the colors helps that a little bit. They're really much better for computers. OK, so this is an interpreter, right? There's many phases that we have to go through. The first phase in any interpreter is lexing. So let's see how we do lexing. Actually, let's not see how we do lexing. Lexing is boring. It's the same in this interpreter as it is anywhere else. So let's skip. Let's go to parsing. Parsing actually does turn out to be more interesting here. So we might imagine what is the type of my parse function. So my lexer is going to produce a list of tokens. Actually, they're L tokens. The L stands for located, because I want to know where my tokens have come from so I can report errors to the user. So we get this list of tokens, and I'm going to produce a UEXP. U here stands for unchecked. We'll see that there's an exp type later that has been checked. But that's where U comes from. But it's this expression type. We'll see it quite shortly. This is no good as the type for my parse, because it doesn't accommodate errors, right? We might have a parse failure, and I don't want to just call the error function. That would be really bad. So instead, I might try this. So it's going to be a list of tokens, and it returns either an error string or an expression. And some people might stop there and be content with this, but I'm never content with that. Because I don't want to just say that it should be any expression. If the user types in x plus 1 on the input line there, well, that's not quite right. We don't know what x is. So I want to specifically say that we want closed expressions. We don't want any free variables. Every variable that gets mentioned has to be bound. And so what I want is that. And I apologize. The green is a little dim up here. It's quite a bit brighter up here. So hopefully everyone can still read that. It's a little dimmer than I'd like. But I want this type. So this is the real type of my parser, is that it takes this list of tokens, and it either produces an error or a UEXP 0. So let's talk about what that is. That's going to be the number of variables in scope that were sort of in scope before I started parsing. So we start out with no variables in scope, so that's why it's 0. OK, so what is this UEXP thing? So here's the definition of part of UEXP. So first off, like every good talk with lots and lots of types, I have my unary natural numbers here. So we have natural numbers either 0 or 1 plus another natural number. And then I use that to index my UEXP type. So once again, this index tells me the number of variables that are in scope in this UEXP. Here, and we'll get back to Finn in just a moment, But so if I have a variable, so this is when I write an x in my program, that's going to be this de Bruijn index. So this is going to be a number 0 or 1 or 2, something like that. When I have a lambda, then I need to know the type of the bound variable. So that's this arg type here. So I'm going to have a type tie that we'll meet later on. And then the function body is going to be another expression. But this has one more bound variable than sort of the outside, right? So in my recursive use of ux, I say suck n here, right? Because there's one more bound variable inside of a lambda than outside. I have let in my language. We didn't see an example of that, but we do have let. And so we have let x equals some expression in some other expression. So the first expression is over here. That has the same number of bound variables. My let is not recursive. If my let were recursive, then this would have the suck here. But then in the body of the let, I do have one more variable. So I have the suck there. It's also worth at this point just sort of calling out my coloring convention here. So we have keywords in blue. We have types in green. We have data constructors, and I think that's burnt umber or something like that. We have local variables in purple, and then there's one or two other colors that will pop up. But one thing that I'm careful about here is to distinguish between types and data. So here, 0 and suck, those are data. It so happens that Haskell now allows us to mix data with types. So I can write suck here in the middle of what would otherwise be a type. But it's actually a piece of data. It just happens to be compile time data. So this disagrees with the way a lot of people describe what's going on. But it's the language that I find is a little clearer around this than talking about promotion and things like that. OK, so I want to go back and describe. Oh, yes, please.
Is the application saying that the ends must be the same there? The application of one thing to another, that the natural number should be the same number?
Yes, exactly. That's exactly what it's saying. So, right, because when we have f applied to x, both f and x are in the same context. There's the same variables that are in scope for both a function and its argument. So that's why we have the same end. Later, we'll see that there's some typey stuff, and we're not getting to types yet. Other questions? Thank you for interrupting me, by the way. OK. OK, so fin, I said that this is some storage of these de Bruijn indices. So fin stands for finite set. The type fin n contains exactly n values. So what that means is, if we just go back here, right? So uvar takes a fin n. So I know if my index n is, say, 2, then my fin n must be either 0 or 1. It can't be anything else. If n is 0, then my fin n can't be anything at all. Was there a question?
No.
OK. OK. OK, so now I have to go through all of these extra words that appear. OK. So anyone who's paying close attention this morning would realize, oh, but fin 0 still has bottom. Yes, it does. Let's just ignore that. We're just going to pretend that that's not going to happen. It turns out in the code, some of these strange pattern match things this morning happen. And so I have to reverse the order of arguments to some functions to get the left to right order to work out to get better completeness mornings. Very sad. OK. So here's the definition of fin. Of all, I spend a fair amount of time looking at these fancy types. Fin always does my head in. So let's just try to understand it by example instead of trying to sort of pull apart the definition there. So let's say I want something of type fin 5. Well, fs, fs, fz, in other words, 2, it has type fin 5. Right? 2 is less than 5 is sort of what I'm saying here. And so the way that we can understand this is by sort of following the types. So here, by the way, I've written 5. I really should have written suck, 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 suck 0, but that's annoying. So I just wrote 5. Let's see, how is this working? We follow the types. So if fs of something has fin 5, well, we see that fs ends in type with fin of suc n. So that means that the n in this outer fs has to be a 4, right, because it produces a 5. So that means that this inner fs has to produce a 4. So that means that this n in the inner fs has to be a 3, which means that the fz, which also produces a suc n, well, that n has to be a 2. Has to be a 2. There we go. So here we can see that if we start out with fz having n be 2, well then suc of 2 is going to be 3, and then fs will take something with a 3 here, and it will produce a 4, and then the other fs takes something with a 4 and produces a 5. Everyone's happy. So now we can wonder about, does 2 have type fin 3? Well, sure it does. Here, the n for fz can be 0, and then it gets incremented 3 times, and we get up to 3. But if we try to figure out if 2 has type fin 2, there's just no way we can get it to work out. Right? There's nothing that we can put here such that when we increment it 3 times ends up with 2. So that's how this type captures the idea of this finite set. So let me just pause here for questions. We're not going to be building a ton on top of fin, other than the fact that it's a finite set. But I'm happy to take questions. OK. OK, so going back to this definition here, so we see because the de Bruijn index is a fin n, then we know that everything has to be well scoped. I can't have de Bruijn index of 2 in a context where I'm expecting no variables at all. That will just be ill-typed. And so once I've produced one of these UEXPs, I know that there can be no out-of-scope errors. It is impossible. Or I would need to have bottom somewhere, but I said we were just going to ignore that. OK, so now that we know the type that we're parsing into, let's just return back to the challenge of parsing. So I said that parseexp is going to take a list of these tokens and produce, if there's no errors, a UEXP0, a closed expression with no free variables. Now, parseexp is going to be some bunch of combinators around I'm using a monadic parser combinator. I think it was parsec. And so I'm going to have this expr somewhere in here, and there's run parsec t or something like that in there. And expr is going to have type parser UEXP0. Well, that's not really going to work out because I need to be able to recursively parse sub-expressions that are not closed. So I don't want expr just to be able to parse closed expressions. I need to be able to parse open ones as well. So that's no good. So then I might think, oh, let me just generalize this. And I want expr to be a parser that can parse an expression with any number of variables n. The problem is that's not really good either. I'm never going to be able to implement that kind of expr because I don't know how many variables are in that output. Right? If you just try to implement it, you won't be able to. We sort of don't have enough information to be able to do it. Instead, what we need to do is now, instead of just having parser, not only do we need to have a parser that produces an output, but we need to have our parser monad needs to be indexed with the number of variables that are in scope. OK, so what do I mean by that? So I think we'll understand this better by looking at what is this parser thing anyway. So it's going to be a type synonym. So a parser NA, this is describing a parser that produces something of type A, and n vars are in scope. And here's its definition. So this is based on parsec t. So that's the parsec monad transformer. It has 4 indices. So the first is the type of the input. That one's fairly straightforward. That's just our list of located tokens. Parsec t allows us to carry around a state. Turns out we don't need that to do our parsing, so we just give it a trivial state. And then a parsec t wraps around another monad. So the other monad that I'm wrapping around is a reader monad that stores a vec of n strings. So those of you who haven't met it before, vec is another type that appears in every single one of these kinds of talks. That it's just like a list, except the length of the list appears in the type. So it's not just any list of strings, but it's a list specifically of n strings. Right? These, of course, are the variables that are in scope. So after I've said \f and then a little later \x to bring f and x into scope, my vector is going to contain f and x. And it allows me, when I parse a variable usage, it allows me to look up which index should be assigned to that variable. But the key thing here is that the length of the vector must match the number of variables that I know I have in scope. So here's the n that comes in from the index to parser. Okay. So here's a quick introduction to vectors for those of you. Actually, how many people have seen this before? Okay, most but not all. So this is another one of these GADTs, right? So if I have an empty vector, that length is 0. That vector's length is 0. Otherwise, I have some other vector of length n, and then the result has one more element in it. But otherwise, right, if I sort of, in different syntax and such, this does look quite like the list type. Okay, so where are we going from here? We're going to this slide. So here's our definition of parser with our var n and our vec. Okay. So let's just recap. So if you got lost there, if it's afternoon, this is sort of one of my summary slides. Okay, so what we've just seen is that I wanted to have well-scoped expressions. My UX type, I wanted to know that as soon as I have a UX, that it was always well-scoped. There could be no out-of-scope variables. In other words, no de Bruijn indices that are too high. And so I did that by indexing my UX, but then we needed to index the parser monad so that I could parse into these expressions. And I had to use a length indexed vector. And that was built on top of my fin and all this other stuff, right? So my first idea was just, I just want to make sure that there's nothing out of scope around here. But then in order to do that, I needed to do all of these other things too. So one of the takeaways, types are social creatures, right? As soon as we start with some types, we want more of them. I don't know if anyone here has tried doing fancy type stuff in Java. So before I met Haskell, I was actually a high school teacher for a while. And so in the American high school curriculum, Java is sort of the language of choice. And I was always trying to sneak more types in because I like types. And if you've ever done fancy type things in languages that don't have a rich type system like Haskell's, you end up hitting these walls, things that you want to be able to say but you can't. And this always makes us want to have more and more sort of power in our type system. So here's something to think about. Sometimes these talks can go on for a long time. If you find yourself getting bored, I have a task for you. So those of you who aren't native English speakers maybe don't know that English has a great deal of fun coming up with fun collective nouns. So for example, we might have a herd of geese. Herd isn't all that exciting. But we also have a murder of crows and a shrewdness of apes. And the reason we do this is just because it's fun. So I propose here that we might have a closure of Haskellers, but I'm unable to come up with a good one for a collective noun for types. So if you want to just sort of ponder that while you're daydreaming, go ahead.
Maybe a paradox.
A paradox of types. But they're no. They're not a paradox. Yes, I have thought about that. A correctness of types, or a soundness of types. I guess we could. A universe of types. That somehow sounds too mathematical. That's not fun enough. Okay, so we have types or social creatures. So let's talk more about them. How do we then type check our language? So I didn't show any examples, but of course this is all type checked. If I had written a type incorrect expression, we would have gotten errors. So the first step is I need to know what my types are. So here's my data type to describe types. Very simple. We have ints, we have booleans, and we have functions. I didn't show any Booleans, but there's if, and there's Booleans, and there's comparisons, all that's fun stuff. OK, so the way that I'm doing this after type checking is I have what I'm calling a type index abstract syntax tree. So just like my unchecked expressions were always scope correct, my type checked expressions will always be type correct. I do not want to permit the possibility of having, say, true plus 1. Right? I don't want to be able to express that in my language. Because if I can express that, then maybe there's some transformation that I have in my interpreter that then violates type safety. Whereas if I know every expression is type correct, then I can't violate type safety. So here's how it's going to look like. So first, I'm going to need to know what the types are of all of my variables that are in scope. So that's a typing context, or CTX, and then I'm just using that as a type synonym for a vector of n types. Right? I'm going to have n variables in scope. Each one is going to have a type, so everything has to work with respect to this context. So this might just list sort of int and bool and int arrow int for the 3 variables I have in scope. So here's my expression type, exp. So my expression type, it works for any n. Right? I can have any number of variables in scope. And it is going to be indexed by a context, a typing context. So I need to know, again, all of the types of my in-scope variables. And every expression itself has a type. And then, of course, an expression itself is a type. So this is perhaps a little confusing. Ty here is referring to this int or bool stuff, whereas type is a Haskell type, sort of some levels crossing a little bit here. OK, so here's a way to understand this. An exp CTX tie is an expression of type tie in a context CTX. For those of you who have seen this kind of notation, right, we could say that if E has the type exp CTX tie, then we have this typing judgment. Right? This is exactly what it means, if you're familiar with that notation. If you're not, I'm not using that notation again in this talk. OK, so again, every expression is well typed in this system. So let's see how we're going to build that up. So we have variables. So here, a variable is going to take this elem. So elem is another way of expressing a de Bruijn index. So what's elem? It's essentially, we could think of elem as a proof that a certain element is in a list, or in a vector in this case. So what we really want to say is that every variable here has to have the type of some element in our context. Right? I described this context as this vector of the types of the in-scope variables. And so I want to pluck one out and say that this variable is that particular type. So that's what this elem type does. So there's 2 different possibilities for elem. This one we can call here. Right? It's saying that x is in the type x cons x's. Right? We see here's x there, and there's x there. So x is in the type x cons x's. It's right here. It's the first element. It's at index 0. So this is my representation for the de Bruijn index 0, saying it's the first thing in my context. Or we have another constructor, which we can call there. Right? An element is either here or it's there, which says that if x is in x's somewhere, then surely x is in y cons x's. Right? We can add another element to our context, and we can still find that x in there. But what that's saying is that actually means look one step further, or thinking of it as a de Bruijn index, that's plus 1. Right? So this is another sort of representation of these unary naturals, but it has all this fancy type stuff. If this is going over your head a little bit, that's OK. We're not building on top of elem here. We just need to know that it's sort of a representation for de Bruijn indices. So here we have lam. So this is our representation for lambdas. So it needs to know the type of the argument. Then we have an expression. Now this expression in here is in an expanded context. Right? So the expression inside of the lambda, it has one more type. It has one more variable in scope. The type of that variable will be arg. So we add arg to the context. And then the result of this lambda, the type of the overall lambda, is going to be a function that takes arg and produces res, where res was the type of the inner expression. OK, so this thing here, this is a singleton. So what a singleton is it's a piece of data that's available both at compile time and at runtime. So in this case, we need this type at compile time because that's the type of the bound variable in my inner expression. And we need it at runtime so that we can print the thing. It turns out that we only need it for printing, which I found quite interesting when I first implemented this. That we can do all the evaluation and everything else without that because this language supports type erasure. There's no type-directed operations at runtime. But we still do want to be able to print it, so it's a singleton. OK, so what do I mean by that? Let's look at the definition of this sty. So the idea is that if our types are either ints or bools or arrows, we need singletons for each of these. So we have sint, which relates to tint, and we have sbool, which relates to tbool, and we have this double colon arrow thing, which relates to the single colon arrow thing. The idea here is that once I know a term, then I know the type, right? After I pattern match and I get sint, then I know that the type has to be tint. After I pattern match on sbool, I know that the type has to be tbool. And so it allows this information to sort of flow back and forth between runtime and compile time. For applications, this one's more interesting than it was for unchecked expressions, right? So here I have the function expression, which has a function type from arg to res. I have another expression of type arg, and that's going to produce an expression of type res. Right, sort of all the pieces connect. Now, if I have an ill-typed function application, this is going to be no good. If I have a function that expects an int, but I pass it a bool, then these two args aren't going to agree, and I'm not going to be able to build my app. OK, this is, I think, the last we're going to see of this exp type before we go on to how we actually type check this thing. Are there questions here before we go on? It's probably worth saying at this point, I am not expecting everyone to leave this room knowing how to do all of this. My goal here is to sort of show that this stuff is possible, that it works, that it's actually fairly clean. And then there's pointers, and I will make sure that code becomes available so that you can access it later. But this is supposed to be sort of an overview. I'm not expecting the full details to get absorbed. I don't think that would be fair. OK, so one interesting thing about this is that, of course, we can even produce this data type. Sometimes, this example of having an indexed abstract expression or abstract syntax tree, this has been around for a long time. But one common criticism of this is, but you could never actually use that in a real compiler, because how do you know that everything is correct by construction? And so one of the interesting things here is, yes, you can use it in a real interpreter, right? So remember, this is a real interpreter. I can just sort of type into it. It's a normal application that does all the parsing and the type checking stuff. And the reason it can do that is, no, we don't know that it's correct by construction, but we have a type checker that checks that it's correct, and then as it checks, it produces the output. We might imagine what that checking function is. So here, I'm just going to leave the monad abstract. We can imagine a monad that has error reporting and I think the ability to produce unique identifiers and things like that. No, I guess it wouldn't need that. I forget exactly what the monad has in it. But it's a monad. It's not very interesting. So we can imagine a check function that takes one of these uexps and produces an exp. The problem is that, once again, we can't really just have this ctx and this tie appear in the output, because maybe my input is an int, maybe it's a bool. We don't know yet. We're going to discover that in the course of type checking. And depending on what we find, that tie has to be different. So this type doesn't really work. What we really want is this type, right? That we know the context coming in because we've seen all the variables sort of up until this point. Then we have some expression, a UX, and then we're going to produce an output type-checked expression for some tie. So this works for any length of context and any input context, but it produces some type out, but we don't know what it is. This would actually work quite well, except that exists doesn't. That's actually an interesting area of research that I'm working on right now with a researcher at University of Cambridge, Neil Krishnaswamy, and a co-author, Joshua Dunfield, have some very interesting ideas for how to get exists into Haskell, but we're not there yet. So instead, we might have to write it in continuation passing style, which is, it does your head in a little bit the first time, but actually not nearly so much as Fin does, at least not for me. By which I'm saying Fin I don't like Fin. OK, so here in check, the idea here is that we have a bunch of variables being brought into scope. But then we have one of these unchecked expressions. And then what we're going to do is we're going to pass our result into some continuation. So here now I can sort of use this magic trick and turn exists into for all, because Haskell has for all. And so if I pass this into some function that runs in my monad and produces a result R, then I can produce that result R. And so this is continuation passing style. And it's just a trick to get around the fact that exists doesn't. I could also use existential data types. That would work just as well. I found when writing this, I actually tried it both ways. I found that doing this continuation passing thing to work a little bit better. It's just sort of syntactic stuff. Everything would work just fine with existential types, if you're more familiar with those. So this is almost the type, but not quite, because there's not exactly enough information at runtime to be able to do this. In particular, you'll see that the input to this function is really just the unchecked expression. I also need to know at runtime the types of all the bound variables. So I need to have information about my context CTX. So to do that, I use this type. So this really is the type. And let's see. So this SCTX thing, that's a singleton for my vector. Right? I need to know the CTX at compile time to sort of know that everything is well formed. And I need to know it at runtime so I can be able to look up variables in the context at runtime. I also need, over here in my continuation, essentially as a result of type checking, I need to get out the type. So again, I can use that in things like printing and error messages and such. OK, so let me show sort of an example of all of this in action. Instead of trying to render it in slides, let's look at some code. Oh, but you can't see anything, can you? Let me do that. There we go. That looks pretty good. OK. Probably want a little bigger, I think. There we go. Is that big enough? OK. So here's my check function. You can see that there's a bunch of monad stuff, but actually here I've generalized this a little bit to use sing instead of SCTX, but this is very much the type that we just saw on the slides. The outer one is specialized just to work over closed expressions, but of course internally we need to generalize it. So I think it's instructive to look at the application case, because that's where a lot of type errors really surface. So coming in, right, we have this UApp. So this is unchecked. We know it's scope correct, but maybe this is true applied to 1, right? That would parse. So that could be the input. And then this K here, people in this room might think that's a kind. No, it's K for continuation. And we also have the context. So this gives us information about the types of all the variables that are in scope. So what I want to do is first I'm going to check E1. And when I check E1, that's going to get me the functions type. E1 is my function, as well as the checked type E1 prime. So if E1 internally were somehow bad, this step would fail. Then we're going to check E2 in the same context right? Because both a function and an argument are in the same lexical context in this language. And that's going to produce the argument type argty and a type-checked type, or a type-checked term E2 prime. So we know at this point that E1 prime has no type errors, and E2 prime has no type errors, but we still have to make sure that E1 prime can be applied to E2 prime. So I have to look. Let's look at that fun tie. Well, I really hope it's a function, right? Not an int. So I'm going to check it. I'm going to check for it being a function. And then if it is a function, now I have to check, does the argument type, that's the type of E2, does that match the expected argument type of my function? Right? If I have a function from int to bool, but I give it a bool, I want that to be an error also. And so there's sort of two checks here on two separate lines. Right? The first is it a function, and do the argument types match? If so, then I can continue. The type of E1 applied to E2 is restie, the result of my function. And then my type-checked term is an application of E1 prime to E2 prime. Otherwise, if any of these checks fail, then I issue a type error. And so here I have this very general, bad function application. I could have, of course, split this up into that really should have been a function, but it isn't, and then a separate error. This is a function, but you have the wrong type of argument. It would be easy to do that. I just didn't bother. OK, so this is sort of where the heart of it is. Now, these checks and my type checker must be correct. Let's say I'm silly and I forget this. Right? So now I've forgotten to check. So now I have checked that it's a function, but I forgot to check that the argument type matches the expected type. So if I save this and then now go over here, let's quit, and cabal build. Could not deduce that the argument was T1 when if T equals arg, and let's see, is there some other stuff? There should be one other thing here. Oh, here, expected type having T1 here, but actual type is T. No, there's something else funny around here. Oh, that's right, T equals arg arrow res. So right, so if we sort of imagine replacing this arg arrow res into this error message, then we'll see that the actual type is arg arrow res, but we were expecting T1 arrow res, and that's because we haven't proved that T1 equals arg. Right? Because my type checker is broken, I've forgotten to do a check, now my code doesn't compile. So I've just eliminated the possibility of a bug in my interpreter. Right? If I wasn't doing all this fancy type stuff, I might have forgotten this. And if I did so, then I would produce bad code. I would accept programs from the user that don't make any sense. Right? If I went into GHC and deleted the line of code that does this, and of course there is just a line of code in GHC that does basically this, GHC would still compile, but now it would accept bad programs. Right? So we don't want to do that. OK, so the reason, again, of showing that is that this is really where the rubber is hitting the road. This is why we do all this fancy type stuff. OK. So I'm going to try to go a little bit faster because I want to leave time for questions. OK, so that was the code. So, so step 4, evaluation. Right? So we've type checked. Now we need to evaluate the thing. Well, actually, this one's really easy. At this point, we have this indexed AST. And so as I'm transforming it from one thing to another, if I make any mistakes at all, I'm going to get type errors. And so maybe easy is an overstatement, but it turns out that doing evaluation with de Bruijn indices is very easy to get wrong. But every kind of mistake I could think of, and I thought of many while implementing this, I was told nice type errors to sort of guide me in the right direction. Right? When I transform the AST from one form to another, I always need to make sure to be preserving types. And even with just int and bool and functions, that's enough for it to sort of know when I've done something wrong. It would be very hard to get the evaluation wrong, but still get my code to compile. So after I got all of this working, I wanted to see, is this actually realistic? Can we do things that a proper compiler or interpreter might want to do? So I implemented common sub-expression elimination. So we can actually, oh no, I'm not gonna bother with it. We can imagine, not imagine. There's a command :CSE in the interpreter that will take an expression with multiple common sub-expressions and optimize it. And even with all of these types, we can do this. And again, there were various pitfalls, but I was saved from all the pitfalls. I didn't have to worry about shadowing. I didn't have to worry about substitution, all of that stuff, because anytime I made a mistake, I got type errors. Much easier to just get type errors up front than having to think of, 50 programs to build a test suite to see if my common sub-expression elimination is working. One interesting part of this is that, as you might imagine, so we're processing this expression, and I need to build up some structure which maps expressions to names, right? So I can see, I've seen this expression before. So we need to have this mapping. So there's in the unordered containers library, we have this hash map type. Well, I generalized it to map from keys to values where the keys and the values were indexed by some other type I, right? So this is going to be the type of expression. And so this meant that it was rich enough that once I identified, this expression is the same as this one, not only do I know that the expressions are the same, but the types are the same, and so I could sort of merge them together. Otherwise, I'd need to use an unsafe coerce somewhere. So the way I did this is I literally took the code from unordered containers, and I just sort of downloaded it from GitHub, and changed the definition of the data type from that to that, and then just kept trying to compile and getting an error, and then just sort of adding what obviously should have gone there. This was really quite fun. It was 2,000 lines of code that I had no familiarity with at all, and it took me about an hour to do all of this, which was great. And the type errors were really quite nice. OK, so pulling out of the weeds a little bit. So again, if you've fallen asleep, maybe now is the time to tune in again. So what have I done here? So in my compiler, now this isn't just even about lambda calculus, but what I wanted to do is I wanted to identify a data invariant. The invariant was that my expressions are well typed. I want to be able to know that that must be true. Then I think up a way of adding more types to my program to check that data invariant. So now I can be sure that that invariant is always true, even as my data evolves. So once I add that to my data type, now I have to prove that my code respects the invariant. So what I mean by this is like in my parser. So originally my UX, my invariant was it's well scoped. But then I had to do all sorts of stuff to the parser to get that to work. Then once my internal expression, my type-checked expression was well typed, then I had to make sure that my type checker was absolutely correct. So that's what I mean by prove my code respects the invariant. And my common sub-expression eliminator had to make sure not to combine expressions of different type from different areas of the code. And then we can repeat. We can look for more properties that we might want to add. So for example, I have not done any invariants in my program that shows that evaluation is correct, right? If I have this big expression of type int, I might accidentally replace that with 5. And nothing bad would happen. But maybe I want to go through and add more types to be able to do that. OK, so this worked. This was actually quite building this. The type errors, some of them were long, but for the most part, they were really quite helpful. There was a few dark corners that I could describe if someone wants, of areas that I think GHC really needs to improve. Although I realize GHC has improved since I wrote this. Since I wrote Stitch in one particular way that really got me. We now have standalone kind signatures, which really, really got me at one point while doing this. So we're ready for this. Now, I will say, I want to connect this back. I mentioned there was this talk earlier from Marco, whose last name escapes me, unfortunately. But he's a Can you say that loud? I don't want to. San Pellegrini. Thank you. Yes. OK. So Marco is a developer at Habito. And his talk was about how it's good to avoid fancy types. And I agree with that too. So I spend a lot of my time hacking on GHC. In the code of GHC, we use very few GHC extensions, right? Because it's actually easier to program sometimes without all of these fancy types. But sometimes it's really important that we have something right, or sometimes we want to express something that's hard to express. So for example, typeable, that's a component of GHC. That has a ton of type extensions to be able to power typeable and typerep to enable dynamic typing. There's a few data structures within GHC that we sort of want to have a little bit more protection around, that we use some extra typing stuff. So the idea here is that it's good to be fancy, but only when you really care about something, right? In my interpreter, if I wanted to sort of change the way information flowed through it, it might be quite challenging to do that at this point. So it's definitely better to write the thing first, make sure you know that it's sort of working, and then add the types later, if you really want to verify it. OK, so I said at the beginning that I spent a lot of time thinking about dependent types in Haskell. So that's sort of my main driver, is that I believe dependent types are the future, and that it's something that, when we start teaching everyone to program at age 10, they should be learning dependent types. We are a long way from that now. But once upon a time, I'm sure people would have thought it was absolutely crazy to think about teaching calculus to high schoolers. And yet that's quite common now, right? So maybe there will be a day that we teach dependent types to 10-year-olds. I hope that happens. So dependent types, so this has grown to a team effort. It really started, I was sort of pushing. Stephanie Wyrick, my thesis advisor, was sort of the force behind me pushing, but it's grown. So here's sort of a small constellation of people who have contributed. This is all just in the last year. So people sort of toward the top and more code, people toward the bottom, more theory. Several of these people are in attendance in this room at the moment. I see two of them right now, Changor and Simon. Ningning is here at Haskell Exchange. I think Stephanie talked about dependent types here last year. Just one thing I would like to comment while this slide is up. So we see here on the slide 3 women. And that ratio of women to men in the dependent types work seems to be much, much higher than in attendance here at Haskell Exchange. So in software, we always like to think when there's a bug, there has to be there's something that causes it. It doesn't just happen on its own, right? So I don't have any grand theories of exactly why this has happened. There's many theories out there. I'm not gonna go into that. And I have every belief that everyone is always wants to be as inclusive as possible. I really do believe that. But clearly, there's something wrong somewhere. And even if it's not us, it's sort of incumbent upon us to do what we can to make it not wrong. Again, I don't know exactly what I mean by that, other than I just want to sort of raise awareness around this. OK, so we've grown to a team effort. Interestingly, dependent types weren't really that much needed for Stitch. We had to use a few singletons. Singletons are sort of a mock-up of dependent types, but it was only in a few places. It wasn't really so bad. So there's lots of activity with GHC proposals that are working in this direction. Some are under discussion right now. So I strongly encourage you, if you're interested in this, to go here and look at some of these proposals. And we do want community feedback because GHC is something we all use here. And as new features come in, they will affect all of us. And so we really do want feedback. There's this proposals process. It's very active. I think it's been supremely helpful in figuring out what's good and what's maybe not as good for inclusion in GHC. So this coming school year, I will be working on GHC full-time. So I'm normally based outside of Philadelphia. This year, I've moved to Cambridge, UK. Cambridge is a lovely place, but in particular, it's where Simon works. And so Simon and I are sort of spending a lot of time confabbing about improving GHC. And I will start to bug him more and more about dependent types as time goes on. And I expect the past couple of years have been a little slow in this regard. I've had a lot of teaching responsibilities. I expect that to lessen considerably thanks to some support from Twig.io. I'd love to have more people coming and contributing to this dependent types effort. Commenting on the proposals is a really great way to start. You don't need to know type theory to be able to do that. You don't need to know GHC internals to be able to do that. Right? You're all users of Haskell. These proposals are sort of user-facing, so please participate. So my goal, so in type theory we use pi to talk about dependent types. So my hope is that we will have dependent types on Pi Day of 2021. So that's still a year and a half away. So right in America, Pi Day is March 14th because we write 3 and then 14 in the date. So that's the hope. We'll see if we get there. I am hoping, I'll say it publicly, so now Simon has to respect this or put it down publicly. I know. My hope is by midwinter to have a dependently typed core language inside of GHC that won't actually affect users at all, and then to sort of work my way up from there. Okay, and that's all I've got. Thanks very much. I'm happy for any questions.
The function check, there was no guarantee that the checked expression had any relation to the unchecked expression.
That's true.
I was wondering if you could also index on the unchecked expressions and if that would be easy.
So not without dependent types. Yes, so just to sort of broaden that out a little bit. So in the check function, of course, I could have just ignored the input and then produced any old properly typed thing as output, and that would still be accepted. That would still compile in GHC. And that's bad, right? I would want to have some relationship between them. Doing that, I think, would require much more power. So I could probably mock it up with singletons, maybe. Actually, probably could. I'd be surprised if I couldn't. But it would be ugly and painful. And so once we have dependent types, we'd be able to do that. Other questions? Okay, thanks all for coming.